Welcome to G Fun Facts Online, where we decode the science shaping our future. Every time you send an email, make a purchase, or post online, you're sending information across a digital world that is perpetually at risk. But what if we could build a network that was fundamentally unhackable? Not through better software, but by using the very laws of physics as its security guard. This isn't science fiction. This is the quantum internet, and it's being built right now. So how does it work? Our current internet, the classical internet, uses bits. Think of them as light switches, either on or off, a 1 or a 0. It's a simple binary system that's powered our world for decades. But it has a weakness. A hacker can intercept and copy these bits without you ever knowing. The quantum internet throws that rulebook out the window. It uses something called a quantum bit, or qubit. Now, a qubit is special. Thanks to a principle called superposition, it can be a 0 and a 1 at the very same time. Imagine a coin spinning in the air before it lands. It's not heads or tails yet. It's a mix of both possibilities. This allows qubits to encode vastly more information than a simple on or off bit. But superposition is only half the story. The real secret to the quantum internet's security is a phenomenon so strange that Albert Einstein himself called it spooky action at a distance. It's called quantum entanglement. When you entangle two qubits, their fates become linked. No matter how far apart you take them, across a room or across a continent, they remain connected. If you measure one and find it's a 0, you instantly know the other one is a 0 too. This spooky connection is what makes it unhackable. Let's say Alice wants to send a secret message to Bob using entangled qubits. If an eavesdropper, let's call her Eve, tries to spy on the message, she has to measure the qubit. But here's the catch. The very act of measuring a quantum state disturbs it. Alice and Bob would see this disturbance immediately, alerting them that someone is listening in. The laws of physics itself blow the whistle on the hacker. It's impossible to copy the information without getting caught. This is the basis for something called quantum key distribution, a way to share secret codes with perfect security. Of course, building a global network like this is a massive challenge. Quantum signals are incredibly fragile. The photons carrying the information can get lost over long distances in fiber optic cables. And you can't just amplify a quantum signal like we do with classical ones, because looking at it to boost it would destroy the very information it carries. The solution? Scientists are developing quantum repeaters. These are like mini, specialized quantum computers that can catch and retransmit the quantum information without breaking the entanglement, extending the network's reach over thousands of kilometers. Despite the hurdles, the progress is stunning. China's Mikias satellite has already proven that intercontinental quantum communication is possible, beaming entangled particles to ground stations over 700 miles apart. Here on Earth, real-world quantum networks are running in cities like New York and across Germany. And in 2025, the focus has shifted from just adding more qubits to making them better and more reliable. So what will we use this for? It's important to know the quantum internet won't replace the one we use for social media and streaming cat videos. Think of it as a specialized, ultra-secure parallel network. Governments and banks, like JP Chase, are already using quantum principles to protect financial transactions. It will allow us to link smaller quantum computers together to create a massive supercomputer, capable of revolutionizing drug discovery and materials science. We could even achieve something called blind quantum computing, where you could run a calculation on a remote quantum computer without the computer itself ever knowing what you were asking it to do. We are at the dawn of a new quantum era. While a full planet-wide quantum internet might still be a decade away, the pieces are falling into place faster than anyone expected. We are moving from theory to reality, building a future where our most vital communications are protected by the fundamental, unbreakable laws of the universe.